Good evening, everyone. I'm Nassim Sirius, the Vice President of Technology Club of Thrace, and I'm delighted to welcome you to today's presentation on air traffic control. Joining me are three esteemed members of the club who will be sharing their experience on this fascinating topic, Giannis, Vassilis, and Fanis. Before we delve into the specifics of the air control, I'd like to take a moment to tell you a bit about our club. Since our inception, we've been a passionate community of technology enthusiasts dedicated to sharing knowledge and fostering innovation. We believe in the power of collaboration to drive positive change, both within our club and our wider society. Our presentations, which we fondly refer to as brown bags, serve as a platform for us to exchange ideas and inspire one another, whether we are meeting in person or online. Today's topic is particularly special as it offers us a glimpse into the interesting world of air traffic control. Our presenters bring a wealth of experience and expertise to the table. Vassilis, with his background as an experienced air traffic controller and current involvement in air operations management software development, will shed light of the complexities of ground control. Giannis, a former avionics engineer, will guide us through the sophisticated onboard systems that ensure the safety and efficiency of air travel. Finally, Fanis, a telecommunications engineer and a radio amateur, will demonstrate how he utilizes an air data receiver to gather valuable flight information. As we proceed through the presentation, I encourage you to save your questions for the end, where our speakers will be happy to address them. But before we begin, I'd like to invite you to engage with us by liking and subscribing to our channel. Your support means the world to us. Without further ado, I hand over the floor to our esteemed presenters. Please sit back, relax, and enjoy the flight, the insights that they have to offer. Thank you. John.
Okay, so can you see my slides?
Not yet.
Not yet. Let me try that again. Screen sharing here.
Yes, we do.
Okay. Now?
Ready to go.
Okay, so the outline of today's presentation will be basically three parts and a bonus part in the end. Vassilis will talk to us about the basics, about what is civilian versus military air traffic control and what's its purpose. He will guide us through the different sensor types and ground systems, and also in the information flow from sensor to controller. I will speak about the onboard systems, namely how the aircraft knows its position and how it communicates it to the ground. And then Fanis will take us through the use of ADS-B and the specifics of the local airport in Alexandroupolis. Finally, we'll close with some insights into the future. So what does the next decade hold in terms of developments in air traffic control systems? So, Vassili, the floor is yours.
Okay. Thank you very much. Thanks everybody for joining. So we will start with slide 3. Giannis, could you please, because I don't see any.
You see my slides?
I still see the first slide.
Which one?
The first one. So is it only me or?
Start sharing and presenting slideshow. Press slideshow.
Should I do it for you?
One moment. View, present. Control F5. Control. Do you see the table of content?
Not yet.
It looks frozen because even your mouse pointer doesn't move.
No?
There's something. Yes.
Okay.
Okay.
This is
Okay,
mine.
I'm moving to the next one. What is
Join-
ATC?
I think I'm sharing the slide now.
Okay, all right. Then you do that.
Okay.
Okay. So basically, what is the air traffic control? Basically, it's a service that is provided by the air traffic controllers to facilitate the movement of aircraft around into the airspace. So there are several types of air traffic control. Depending on where the aircraft is and what the type of aircraft is, we have civilian ATC that manages the movement of commercial planes, but also of military planes in the airspace over a country or a region. And the air traffic control is typically managed by government agencies or by contracting agencies in some cases. Then we have the military ATC. So the military is able to also to control aircraft, but in a different way. So typically in the military, we also have air traffic controllers like we have in the civilian world. Like, for example, we have ground controllers and approach controllers that work in military airports, where typically they also support civilian flights, like, for example, the airport of Kalamata. But we also have command and control centers. What we used to call ground control intercept now is a full air that also does some kind of traffic control, but it manages more the movement of the military aircrafts, but also surface-to-air missiles against targets in the air, on the surface, and on land during peace, crisis, and war. The military ATC and the military command control systems are managed by the military branches of a country. It can also provide air traffic control services to civilian aircraft in times of emergency. And the difference between one of the differences between military ATC and civilian ATC is the classification and how the information is shared to the public. So the military ATC, of course, is often classified, and because it involves sensitive information. Also, the military ATC provides flight information to military aircrafts flying outside the assigned areas, and it does provide close control to military aircraft inside the assigned areas. So my background is more military ATC and more command and control systems. So I was a radar controller and an intercept controller in my previous life. So what we were worried when we had military aircrafts under control on a frequency was that they fly safely to the assigned area where they had to conduct the exercise, and that when they arrive in the area and they were fully under control, that they do not violate the block altitudes that they were assigned to, and they did not violate the 2D borders of the area. So they didn't go out of the area, and they didn't approach military traffic that was in the vicinity of the area. And we were always giving them directions and bearing and range and distance to the civilian traffic flying around, so that they can also establish radar contact with their own radars or visual contact if they could. So the flight phases. So from the pushback of the aircraft from the gate of the airport to parking to the next gate at the other airport that could be at the other side of the world, we have basically three phases and three types of controllers that control a flight. So we have the tower controller, which is the person that provides the service in the vicinity of an airport, of an aerodrome. And then we have the approach controller. No, the tower controller also controls the aircraft on the ground, and and until the takeoff. Then the approach controller or the departure controller is the person that provides the air traffic control for departing and arriving flights. And they are the link between the tower and the area controllers. And then the aircraft is handed over to the area controller, which is also called the en route controller, who's the person that normally serves the flight during the cruise phase. As you can see, the cruise phase is in the middle of the presentation there. And of course, it is the biggest part of the flight, where the controller is actually passing through different FIRs and different ATC areas, and it is handed over from one controller to another controller that could be to different countries. And the handover nowadays can be done via voice, can also be done, as we will see with Ioannis later, using automated systems, something like using a text service where the aircraft is actually alerted and instructed to contact the following controller on a specific frequency. Okay, next please. So ground systems. So what do they use? What do we use in the ATC to actually communicate with the aircraft, to actually visualize their trajectory, to see where they are, to see who they are? Next slide. So typically we have sensors, we have radars, we have primary radars, secondary radars, and other types of sensors that are able to detect an aircraft. So we have two basic types: cooperative types and non-cooperative types. Cooperative types are like secondary surveillance radars, secondary radars as we call them, in the that interrogate an aircraft for a specific IFF-SIF mode. The IFF-SIF modes that are used by civilians are the 3 Alpha and the 3 Charlie and the mode S. And the IFF-SIF modes, mode 1, 2, and mode 4 and 5 are used by the military. Then we have the automatic dependent surveillance broadcast, the short for or ADSB as we know for short, which is a system that is used by the aircraft. It's not it is not like the IFF-SIF that where the radar needs to interrogate the target. It is a continuous transmission of data from the aircraft, where various information about the flight, like the speed, the heading, the altitude, the position, of course, settings like the selected altitude in the autopilot or even the vertical rate of the aircraft are exchanged. Transmitted. We have the airborne collision avoidance systems, which is a system that is used by aircrafts and by ground controllers to basically to detect collisions between aircraft. So and it also instructs the aircrafts to perform avoidance maneuvers in case of a collision detection. And then we have non-cooperative types of sensors, like the primary surveillance radar, PSR as we call it, which basically does not, the non-cooperative types of sensors do not rely on the aircraft cooperating with them. So it is also valid for aircrafts, for military aircrafts, for example, of nations that do not use IFF-SIF and do not use ADSB, and you can also detect them, of course, if they're not stealth, using PSR radars. So we have precision approach radars that are used in airdromes, which basically are two types. They have two types of antennas, one that scans the elevation and one that scans the horizontal position of the aircraft, and they are determined then to guide the aircraft with precision for the landing. And then we have passive sensors that use multilateration technologies. We have MLAT with ADS-B and mode S transmissions. We have also multilateration based on the reflection of civilian signals like television signals, FM radio signals, cellular phone base stations, and basically any type of radiation that can be reflected by a flying target can be multilaterated. So next one, please. So a little bit about the IFF. The IFF is working at the 1030-1090 megahertz range. Not range. It is 130 and 190. It is not a range. It uses these two frequencies. And as I said before, for civilian usage, typically it contains mode 3 and mode Charlie. Also, it contains mode S. And we have nowadays the IFF emergency codes that the pilot can set, which is 7500 for hijacking, 7600 for loss of communication, and 7700 for general emergency. We also have, but it's not very common, the 7400 that is used for the loss of communication of drones, basically, nowadays. Next one. So, how do we create tracks, and what is a track and what is a plot? A plot is a target report that results from digital integration of the received echoes or replies inside the antenna beamwidth. Normally, when a radar scans the area, it gets back a signal from the aircraft. Okay, either the reflected signal from its own radar, in the case of PSR, or the reply of the IFF SIF equipment of the aircraft in case of an IFF interrogation. Okay, what it determines by the signal is the azimuth and the distance, and also the altitude. If it is a 3D radar, the altitude of the aircraft. Okay, and this is basically what a plot is. A plot is a piece of information that contains the time of detection of a flying object with its azimuth, its range, and its altitude from the sensor. Of course, it contains more information, especially on SSR replies, and which is the information that is included in the SSR reply, like the mode, the IFF SIF modes, the mode S, and other information. So how do we go from the plot to the track? What is a track? A track is a target report resulting from the correlation by a special algorithm of a succession of radar reported positions for one aircraft. So basically, it's like if you're given successive pictures of a car passing in front of you, you could, as a human being, say, hey, that look, this car moves. This is a car, and this car moves because I see it here, and then on the next picture I see it like 5 meters further, and then I see it 5 meters further, and I see it 5 meters. So this is a correlation of all these plots, okay, all these observations into a moving object, and then you create a track on top of it, and you say that this track is now a car, and it has this heading and this speed, okay, and it is at this altitude. So this is basically how the tracking works. Okay, the tracking, of course, is much more complicated, and it involves a lot of mathematics, and basically it has two bigger problems. One is the data association. So when you get a target report, a plot from a radar, then you need to figure out if this is a new target that you haven't already generated, or you haven't converted it to a track. Or is it a detection of a track that I already have in the track store? Okay, so this is the data association problem, and sometimes a track in the track store can be associated to multiple plots that you receive around it, and then you need to figure out which one is the actual detection for this target, and if the other 2 or 3 that are associated are detections for neighboring targets or are new targets that haven't initiated yet. As you can see in the picture, the blue dots are let's say the plots, and the green one is what the tracker is actually producing using the Kalman filter from these observations. Next, please. So multilateration is a different technology. It's non-cooperative, and it actually what it does, it calculates the time of difference of arrival, the time of arrival, but basically of a signal from multiple sensors. Typically, we need more than 3 sensors, 4 or more sensors, basically, to perform multilateration. And they need to be very well time synchronized. Okay, what happens is that for each of the detection there is an area that is the area of probability where the target is based on the time of arrival. And if you combine all these areas together, then you have the common area which identifies basically the place where the aircraft is flying. Next one. So then all these signals, they end up in the air traffic control center, and we use specific protocols to convey plot information. Okay. Nowadays, the most common one are the Asterix category, the Asterix family of protocols. We use categories 1 and 2, categories 19 and 20 and 21. So 1 and 2 is a plot type category, an old one, the old one. 48 is 34 and 48 is a successor category for 1 and 2 for plots. And then we have 20 is the multilateration category, 21 is the ADSB category, and 19 is the service category for multilateration. Basically, it gives you extra information about how the targets that you get in the multilateration were produced, from which sensors and stuff like that. And then we have category 62, which is a track category, and it is used by ATC systems to exchange initiated tracks with each other. These categories are also used by the military. Okay, I'll talk about it later. Then we have raw ADSB that is used. Basically, we have the radar cape and the beast, which are the same protocol. Actually, these are the receivers. Okay. But the difference is that the beast receiver normally is a USB receiver, and it contains a timestamp that is not as fine and as accurate as the radar cape timestamp, which is produced by the embedded GPS. Okay. And then we have military protocols. I'm not going to refer to protocols because I don't even know if they are classified or not, or if it is classified. The one that is for sure not classified, but I haven't included, is the RSRP, which is the radar for Southern Region and Portugal, which is extremely common around NATO, and other types. But nowadays we mostly use military categories of Asterix. So we have military categories that we have identified for military use of Asterix, namely category 159, and we also use civilian Asterix categories, because in the military we use both military radars and civilian radars to perform tracking. Basically, we don't only use the military radars, we use military and civilian radars, and most of the time the civilian radars are much better. Next, please. So what do we see on a radar screen? Okay, on the left, we see typically a civilian track. You see the speed vector, you see the track symbol, and you see the history dots, which are basically the position that it occupied in the past for every update. And then we have the label where you see the altitude, the call sign, and if it is climbing or if it is descending. On the military console, on the other hand, we are interested in both the track and the plot. And the reason why we're interested in the plot is that we have to deal with military aircraft, and especially in crisis and war. These are not cooperative aircraft, so most of the times you don't have any information from secondary sensors, and you have to rely on primary sensors. And with primary sensors, we have a lot of noise, we have a lot of clutters that are produced, and these clutters make tracking difficult for systems and makes also tracking not very reliable as it is with secondary information. It goes without saying that if you get a bunch of information without any label on it, it is more difficult to see how many aircrafts you have and which plot belongs to which track than it is when you have the same information but with call signs. Of course, when you have call sign, it is easy to see, to associate as we talked about the data association problem with trackers. So it is easier to associate an SESAR plot that has tracking information, that has call sign information, to a track that has already the same call sign, than it is to associate the track with no information about who it is with a track that also has no information about the call sign. Okay, so we display both the plots and the tracks that are produced. As you can see, there's also a almost straight line of blue dots, and this straight line of blue dots is the ADSB information, okay, that we display. So now you see that the white dots are the plots as we receive them from the various radars in the history, in the past couple of minutes, as we can see here. And from this information that is a little bit scattered, as you can see, we do produce a track, and the track is very close to the ADSB. So in this case, the tracker is doing a very good job into tracking that flying object. Next, please. So now I leave the floor to Giannis. Thank you very much.
Yep. So we're going to talk about the onboard systems. I'm going to talk to you about that part. Before we move on to the onboard system, a small clarification. So the basic job of a tracker, in case this was not obvious, is to effectively correlate the raw information, and instead of having many different blips on the screen, to actually indicate that these all belong to a single aircraft and maintain a track over time. So to continue tracking the blip from the previous cycle to the next, so that the controllers don't have a lot of noise and a lot of ambiguity in what they see. Fanis, shall I present, or you will show my slides? Okay, let's talk about the onboard system.
I can do it for you, or you can take over if you like.
Okay, you do it if that's okay.
All right.
All right. So onboard systems. As you might have noticed, modern aircraft are pretty busy with a multitude of antennas. This is just an indicative diagram of a standard airliner, Boeing 787. And the reason why we're showing this slide is to walk around the plane and see a little bit the individual systems and notice a few things even before we go into the details. So first of all, modern aircraft usually have both voice and data communications. In the past, we had only voice, but more and more systems are switching for voice to data for reasons of error correction and efficiency and reduced crew workload. Also, one thing that you might notice in this diagram is that many antennas appear on the top and also on the bottom of the plane, on the back and in the belly. And the reason for that is that you can not always rely on the fact that a plane will be flying straight. So if you want to have good VHF radio reception, you have to make sure that at any given point in time, at least one of the antennas is facing towards the right direction. This applies for GPS, for emergency transponders, for automatic direction finder, and so on and so forth. Also, since modern aircraft have different radios that transmit in different frequencies, most usually we find small VHF antennas attached to the hull of the plane because of the frequency they can be smaller, whereas the HF antenna, because it transmits at a lower frequency, has to be larger. And usually we hide it in the tail on the vertical stabilizer of the plane, which is a nice spot, not obstructed by the body of the plane, and also it gives you enough length and enough vertical space to fit an antenna on the leading edge of the vertical stabilizer. In this plane, apart from the normal voice communications like VHF and HF, we see a lot of antennas for navigation aids. So you will notice the DME, which is the distance measuring equipment. We'll talk about this on the next slide, the one after. And also the VOR, which are standard nav aids, which assist planes to determine their distance from an airport and their orientation, their azimuth to that. You also see in the front antennas for the weather radar and the ILS glide slope and localizer, which is a system that the airplanes use when they are very close to an airport to be able to follow exactly the descent trajectory that is needed in order to touch down at the runway smoothly. And you also see a newer generation of systems, which are high-speed data links, which are utilized when the plane is actually parked at the gate. So whenever a plane is parked and docked to the airport building, apart from passengers unloading and offloading and supplies and luggage being offloaded, the plane takes this opportunity to download maintenance logs, to receive systems updates, and also to update the media library for the entertainment system. So there are essentially Wi-Fi links which allow the plane, when it is parked, to exchange a high volume of information that it cannot exchange in flight. Now, this is more or less for airplanes. For helicopters, we have a similar set of systems. Their positions are also follow the same rules. So you will find the VHF antennas, both top and bottom, to be able to ensure good transmission and reception. You will find automatic direction finders and VR DME antennas also to assist with the navigation of the aircraft. And also in the belly of this helicopter, for example, you will see the transponder, which is the IFF antenna, what Vassilis already spoke, where this helicopter will respond to queries from a radar station about its ID and altitude and speed. Also, there is an antenna on top of the cockpit, which is for the emergency transponder. And usually these systems have antennas at the top of the aircraft because it is the last part of it to sink. We want to maximize the probability that it will continue to emit even if it ditches in the sea. Now, moving on. Next slide, please, Fanny. The first set of systems is the navigation systems. First of all, you need to know where you are before you can communicate it to the controllers on the ground. Traditionally, we have had multiple generations of such systems, and the important thing to remember is that at any given point in time, you have many generations of aircraft flying around. You have machines that were built in the 60s, in the 80s, and also mixed with airplanes that have been built in 2023, for example. They carry different systems. Some of them are more elaborate, more complex, more advanced. Some of them are pretty legacy and rudimentary. The point is that we don't rely on a single specific system. In order to do air traffic control, we just need to get the right information, a minimum set of information to be able to determine where the airplane is, which way it's flying, and if it is more or less following instructions. we don't want the most advanced or the latest systems necessarily. We just want a subset of the system that will deliver to the controllers a minimum set of information to run their processes. So one of the oldest systems was LORAN. LORAN is basically 2 radio emitters in high towers. You can think of it, if we think the equivalent in light beams, it would be 2 lighthouses. It was used since Second World War to basically do a very crude location and direction of aircraft. And you could do that by comparing the signal that you receive from 2 points in time, and this allowed you to determine if you are roughly on the right route. It wasn't very accurate, but it was accurate enough for Germans to direct V2 rockets right into the center of London from France or from anywhere. This is not used anymore as far as I know, as a rule. Then we have the DME and VOR, which is distance measuring equipment, and VHF, what is O is ranging. VHF omnidirectional range. These are also relatively simple transmitters that you find at the far end of a runway or at certain waypoints, which are turning points, waypoints for aircraft, not necessarily attached to an airport. And they are allowing planes to tune into the frequency that these 2 navigation aids transmit, and then see display on the cockpit on an instrument that is called Automatic Direction Finder, ADF, the actual direction, the actual vector to reach that destination. So the pilot can tune into a specific frequency that is referred to in his charts as the frequency for Alexandroupolis Airport, for example, or for an Navaid in Crete, and the arrow will point him to fly to that direction. The cool thing about the ADF is that it is AM modulated, which means you can even tune into a radio station and the ADF will point you directly to the transmitter. Also, more modern systems. Most aircraft nowadays have a radio altimeter, which is a very small directed antenna that is pointing vertically at the underside, at the belly of the plane, and it allows the plane to determine its altitude very precisely. Planes have other instruments to help them determine their altitude, like barometric altimeter, but these tend to drift with time and changing weather conditions and are not as accurate as radio altimeters. The drawback with radio altimeter is that it is pointing vertically, so it is not really helpful if you are going to crash on a mountain ridge. It will be too late by the time it detects some altitude change. Now, in terms of the most modern systems, INS is what we used to have since the 1960s, 1970s. It is basically a gyro, like the one I have here. This is a pretty ancient mechanism that if you turn it at high speed, using a string or something or electrical motor, it tends to maintain its attitude. So the point is that no matter how the plane turns, if you have a gyro installed on the plane, you can determine always which way it is facing. And also gyros can measure acceleration very precisely. So if you calculate the integral of acceleration, then you can get the exact speed. If you calculate the integral of speed, you get the displacement. So this way, by constructing very precise gyros and very good analog integrators at first, because most planes from the 60s and 70s had actually analog computers, you can calculate where the plane is in space and how much it is accelerating and what was its speed at any given point in time without the help of any external antennas or other equipment. So this is the benefit of an inertial navigation system. And the drawback is that it is drifting with time also. So the more you fly, its precision is dropping. but it is a pretty reliable system to fly multiple hours or thousands of miles away and still get a decent reading. Modern inertial navigation systems don't rely on mechanical gyros anymore. They actually have laser gyros, which are effectively 3 laser beams perpendicular to each other, which measure the reflection on a small mirror and then can determine the acceleration and attitude. Finally, we have the GPS, which I'm not going to need to explain in any detail because we all use it in our phones and cars any day, anyhow. The drawback of GPS navigation, which we don't notice very often, but which Fanis brought to my attention some time ago, is that there are places in the world where the GPS is not reliable, not working well, and probably this is deliberately close to theaters of military conflict or in countries which do not have good infrastructure or reception. And next one. Now, once we know positively our position on 3D space using any of the systems that I mentioned, with various degrees of precision, then we can start thinking about how we can communicate it to the ground. Now, the obvious way to do this is to pick up the headset from the pilot and actually, as a pilot, and speak to a ground controller. This is not the most efficient way, but this is how it used to be done and how it's still done in airports that rely only with VFR guidance of planes around the terminal area. Most planes have a pair of radios. These are 2 completely identical radios. For civilian aircraft, these are VHF radios emitting on part of the frequency that is of the frequency spectrum, which is called airband. So for civilian flights, this is from 108 to 137 megahertz. And for military, the military planes have VHF, but additionally they have UHF radios, which use another part of the band, 225 to 399 megahertz. Right in the middle of those ranges, there are 2 very special frequencies which are reserved for emergency communication. So everybody is listening on those frequencies, but no one is allowed to transmit unless they are having an emergency. These are called guard frequencies. They are 121.5 megahertz and 243 megahertz. And for simplicity, the one on UHF is exactly the double from the guard on the VHF. There is a similar frequency, incidentally, for maritime communications. It's maritime channel 16, I think it's on VHF, and that one is designated for maritime emergency. Now, these radios have 2 interesting characteristics. First of all, they are AM modulated in an era where very few things are AM modulated, and also they are pretty weak, surprisingly weak. So why AM modulation? The reason is on one side historical, because this allows compatibility with very, very old aircraft and very, very old radios that have been flying for half a century. And AM receivers are also simpler and more energy efficient. But most importantly, the reason for using AM modulation is that if it happens that 2 aircraft or 2 ground stations transmit simultaneously, the reception will not be garbled. You will be able to hear at least one of them, either the closest one or the strongest transmitter. So one of them, you might have noticed that when you listen to AM radio, for example. Always you can listen at one station. In FM, if 2 stations are by accident too close for some reason, you might have artifacts of one station affecting the reception on the other. Now, with respect to power, most aircraft V or UHF radios are pretty weak, 25 watts. This is the equivalent of a radio that you would find on a standard police car. but they still manage to get across pretty good, pretty clearly, because they have a hidden ace, which is their altitude. So if you are on top of a standard apartment building and you're, let's say, 20 meters up in the air, you have a line of sight of, let's say, 18 kilometers, and this effectively limits your reception, apart from the occasional obstacles that the signal will find along the way, trees, buildings, mountains, and so on. If you are at a standard cruising altitude of 30,000 feet, which means 10 kilometers up in the air, you have a line of sight of 400 kilometers. And if you do the math, this translates to 150,000 square kilometers, which is the average size of a normal European country. So effectively, you are so high up that you can reach far away, even with a weak 25-watt VHF radio. Next one. So now that we sorted out how you could communicate using voice, the natural evolution for that was to switch to data communications. So data communications is when the aircraft can transmit a pulse train, a modulated signal, a digitally modulated signal, which contains some essential information. One such system, which Fanis is going to demonstrate to us also, next, is the Automatic Dependent Surveillance Broadcast, ADSB, which transmits periodically at 1090 megahertz a small set of key information about the aircraft, about the flight. So there you can find a standard unique key, a hex ID, the call sign, the registration of the plane, which is, let's say, its license plate, what you see painted on the fuselage, its type, the IFF code, which is shown as SCOAC code here, and then some basic information about where it is and where it's flying to and at what speed, and also some basic measurements for the wind as measured by the aircraft's instruments. One thing to remember is that an airplane is not always facing the way it's flying. So depending on the direction and speed of the wind, an airplane could actually be flying with a high angle sideways. Next one. So speaking about data communications on board modern aircraft, another system that we have is ACAS or TCAS, depending if you are which generation is installed and if you're in Europe or in the US. This is the aircraft collision avoidance system. Effectively, this is a smart way to utilize information that we already had. So since we have IFF information, since the planes already had transponders to be able to receive and send IFF and ADSB information, somebody had the bright idea to save that information. So not only maintain a single query, but store it in the airplane's computer and start running calculations. So if you have enough data of those two systems, then you can create a 3D map and you can start calculating trajectories of the various aircrafts that have reported the position around you. And then you can predict collisions and then alert, like Vassilis said, you can alert the pilots to divert. The way this system is working, it defines 3 areas. The green one, like you see on the left side of this slide, which is pretty far away, 20 nautical miles. And then a closer one at 3.3 nautical miles, which corresponds to 40 seconds reaction time, and then a really close one, which is 2 nautical miles, which is a little more than 25 seconds. When another airplane enters the yellow area, you get an advisory, you get an indication on the screen. When it enters the pink area, you actually get a voice alert and specific instructions to deviate to a specific direction. So the system is smart enough to instruct one plane to dive and go right, and the other to climb and go left, for example, so that they don't deviate at the same direction and then not avoid the collision. One key thing to remember is that this system is not a radar. It relies on responses from the surrounding aircraft. If something is not emitting its position on IFF or DSB, it will not be visible to this system. So military flight, a balloon, a drone, or whatever else might be in a normal plane's path will not give an indication to ACAS if it is not transmitting data. As a side note, civilian aircraft don't have a radar capable of seeing other aircraft. All radars might appear similar to us, but actually there is a big difference in price if you want to distinguish small metal objects far away in the sky, or if you just want to see a big storm in front of you. Most civilian aircraft have weather radars, which are there just to warn you that there is a significant weather ahead that you need to avoid. Now, moving on, another system of data communications on board the aircraft is ACARS. I know the name is very close to the previous system, but this one is called Aircraft Addressing and Reporting System. You can think of it effectively as SMS capability for SMS capability for airplanes. It can send small text messages, either free text or formatted with specific data and format, using the existing VHF radios of the plane. And it is used for a handful of basic scenarios. So first of all, it transmits automatically the key information about flight phases. So when the plane pushes back from the gate, when the plane takes off, when it lands, and when it is back plugged into the gate. These are useful to determine departure and arrival times, the crew's salary, and overall maintenance and refueling windows. It is also used to receive and transmit flight plans and weather. So if a plane needs to redirect mid-flight, perhaps it can send a flight plan by just typing into this multifunction display and send a message to ground control. And it can receive weather updates through this screen. Also, this system sends some small health information and events about the aircraft itself. And it can send ping and heartbeat information, like to let the ground stations know every X amount of seconds that it is functional. Finally, it can send free text, and it's not uncommon for pilots to signal the arrival airport that they have, for example, a security issue on board or a disturbing passenger, a drunk passenger, so that they need assistance on arrival, the police or an ambulance or something like that. Now, this system is something that you could also monitor at home. Actually, this piece of software is something that you can run using a small software radio receiver, like the one that Fanis is going to show us. And it actually decodes these messages at this specific frequency. And you can actually, they're plain text, they're not encrypted. You can read them on your computer. So effectively, you can snoop in the communications between the aircraft that are overflying your area. Next one, Fanny. Now, one of the latest systems, latest by aviation terms is last decade or 15 years, is on board satellite links. What we used to have until 2015-17 was data links provided by two constellations, mainly Inmarsat and Iridium, and they could provide at best, under certain conditions, 700 kilobps to an aircraft, and that was used for various purposes, either as an auxiliary data link or to sell internet services to passengers. Now Starlink is also selling a variant that can be installed on airplanes. It can reach up to 30 megabits, which doesn't sound much, but you have to take into account the difficulty of running a steerable antenna on top of a moving target. So because Starlink works by having the ground antenna point at an overflying satellite, it needs to be able to precisely track the satellite in order to be energy efficient and to ensure a good signal. When the customer antenna is also moving, as in the case of an aircraft, then you have to account for relative speed and also the turns of the airplane, and it is much more difficult to track and do handovers. So we are effectively limited to 30 megabits per second, which is already a pretty significant bandwidth to be able to receive on a plane. Next one. Another form of data communication that aircraft have is the emergency transponders. So under normal conditions, they're not used, they're just tested, but they are very useful when things go south. They are automatically activated either in collision or in contact with water. And actually, ships also have these transponders installed at the bridge, because if the bridge takes on water, it means that the whole ship is already underwater. They transmit the position and ID of the craft that has an issue or that has crashed. Firstly, to satellites at 406 megahertz. There are multiple satellite constellations, older and newer, that actually monitor these frequencies and forward this information, so the position and ID of the aircraft that crashed, to a national coordination center. This is usually called Joint Rescue Coordination Center, and usually it is part of the Coast Guard or Navy of each country that has a responsibility for search and rescue within its territorial area. In Greece, this is called XED. It's Κέντρο Συντονισμού Έρευνας και Διάσωσης, and it's in Piraeus. They also transmit to local search and rescue teams, like a helicopter that goes to search for a downed plane in the standard guard frequency at VHF at 121.5 megahertz. Next one. Now, the last data communication system that I'm going to talk about is the engine diagnostic data links. This was actually, I wasn't aware of this either, but it became pretty famous when the Malaysian Airlines MH370 flight went missing a few years ago. Now, if you remember by following the news, that story, we still haven't figured out what happened to that plane. But most likely, one of the pilots was determined to commit suicide, and he had deliberately disabled all the communications on the plane. So there is an easy way to do this. You just pull the circuit breakers, and this should work. But what the pilot wasn't aware of is that the engine manufacturer had actually put global monitoring on board the engine. And the reasons are multiple, so that they can collect a lot of information to improve their engines or to be proactive about maintenance when something goes wrong. But effectively, if you're selling something that is so expensive, the normal aircraft engines for airliners cost between 25 and 45 million apiece, then it is pretty cheap to install a small iridium modem right next to the engine fan and have it transmit information back to the manufacturer, no matter if the engine is flying, if it is on the ground, if it is under maintenance. As long as it gets power, it will transmit. Now, what we have to remember is that this system was not built to transmit position or speed like the systems that we spoke before. It is just there to transmit engine diagnostics. But because of the reception characteristics of that signal, so they were able to plot some potential positions for the plane, so that that signal could theoretically be received by one of the satellites. And this is actually the best information that we have about where that flight ended up. Engine manufacturers nowadays are running global operation centers. For example, Rolls-Royce has one in Coventry in the UK, where they monitor all the engines that they have sold through these systems. And you can think of it as engines by themselves without aircraft, just reporting their vital data back to the maintenance facility. Next one. So now it's Fanis' turn to show you what someone can do in practice.
Yes. everything that we heard from the other two friends of us is very interesting. Is the theory. Now it's time for us to see some practical things that we can do and how we can receive all these signals. Nassim, I have something for you. You should put somewhere up here a link with the other video that we have about the SDR receivers, so we don't have to talk about it anymore. So we can move on. Using an SDR receiver, normally USB dongle, like the one we see in the presentation. The only thing we're missing is an antenna, which we can effectively create by ourselves. I have some simple diagrams on top of the presentation that everyone in our group can do in their spare time. Of course, you can buy a ready-built antenna and have a better reception, but one of these antennas can do the job for you. With the SDR receiver, the next thing that we need is the decoder. The decoder is a software that we're gonna use that will decode the signal we receive from the airplanes. Normally, the two most famous decoders that are used, and they are open source, and you can download them on the GitHub, is Dump 1090 and ReadSB. Both work very well. Some prefer one over the other, but it really doesn't matter which one you use. The decoder can run in any software. Either you have Linux, either you have Windows, you have Mac. People prefer Linux because it's free and easier to install on it. Many Docker images are available from companies that you can use and run it on a Docker station as well. A simple P02 can do the trick, and you can decode the signals and plot them in the map. Another open source software is TAR 1090, which also is used to create a nice map where you can see all the details from the ADSB information, and we're gonna see this software in action later on our demonstration. Furthermore, what you can do with your data is you can share your data, send it via the internet to central big websites like FlightRadar, ADSB Exchange, FlightAware, etc. And also your data that is sent out is sometimes used in MLAT in order to calculate information about the position of aircraft, that they are not transmitting a full ADSB signal, but they're transmitting a mode S or mode alpha, as Vassilis and Giannis speak before. You can receive the signal, and using Multilateration, the big websites, all yourself, if you have multiple receivers, you can pinpoint the location of the aircraft. Furthermore, I have some screenshots of my receiver, where we can see some what we see here is the standard arrival on Alexandroupolis Airport. On the left is the chart that the pilots have. I don't know if this one is outdated or not, but it is okay for our presentation. What we can see on the top middle is all the route that the aircraft has followed in order to have a landing. The black dot that you see on these images, and later on other similar ones, is the location of my receiver. So we can see that everything is the top picture is according to the chart. On the middle bottom picture, sometimes if the weather permits it, pilots communicate with the tower, the ATC, and request a visual approach. So when they do that, they do not follow the chart, but they visually approach the airport. So you can see that they follow a different route. On the middle right picture, we see that the aircraft, which it's a small aircraft with propeller engines, probably Sky Express or maybe I don't know, had arrived at the airport using the standard Limnos 1 Alpha approach, but when leaving for Athens, what we see is it encountered some bad weather, so we didn't follow the standard traffic route and deviated. Using our software, we can see real time, so the radar data weather as well. So we can verify that why this airplane has deviated its course. What's next? Now we have a departure from runway 25. What we see is the CMB 427 doing a very nice and accurate departure according to the chart. But at the same time, the ATC was very busy. It had another plane, an Aegean flight, approaching the Alexandroupolis airport. And also it had two small aircraft that they are from the training school, that they had to hold their position on the north of the airport. On the bottom right, you see that Aegean flight, as well as the United States flight, they actually are on the same track. Aegean flight is flying on 30 degrees angle, 30.6 degrees angle, and the Boeing 747 is flying on the 210 degrees angle. This is one flying against the other. What separates them is that normally the ATC will guide its plane to hold a specific altitude. We see that the Aegean is holding 11,000 feet. The Boeing will hold something lower, and as soon as they clear each other, they will inform the tower that they have cleared, and they will receive further information in order to continue their journey. Using an ADS-B receiver, you can see on the bottom left picture that we can track the plane on the runway, even after its landing. Sometimes the big websites they do not show this information because they feel it's not accurate. But using your own receiver, you can always get this information and plot it on the map. Aegean on this particular time has landed, fully landed in the middle of the runway. It's where the orange line ends. Then stopped and made the 180-degree turnaround and taxied via Bravo in the terminal. Let's see. Let's move on. This one is a very interesting one. It was one that was really. I was sitting in in the television watching something I can't remember now, and it doesn't matter. And suddenly I had an airplane passing above my head, which is very unusual because the route of an airplane is not from this direction. So I went on, jumped in, went to the computer to check what this airplane is and if my ADSB receiver is receiving it. I was lucky enough. This airplane was received my ADSB receiver, and we have it here to show it. The day was the 25th of November 2023. And on the top right, you can see the meta information that the airport was giving on that day. This is each airport is transmitting periodically. I think it's twice in an hour. Meteo data. They called METAR. And if we decode it now together, the first line 25/19/20 Z means it is the 25th day of the month. The hour is 19:20 in UTC time. This is specified by the letter Z. Second line, it's about the wind. The wind is from 200 degrees direction. It is 20 knots, the 20 after the 200. The G33 means that it has gusts of 33 knots, which is the direction. As you can see, and if you make the change it to any other scales that you understand, 33 knots gust is a very, very strong wind. It's not easy for an airplane to land with these gusts, and it can easily move it out of position. This airplane, starting from the top left, going following clockwise the pictures, you can see it made 3 different attempts in order to land. It must have been very terrifying and for the people, because we're not used in Alexandroupolis to have failed approaches. But this is what happened, and we have it in picture. I think it was really terrifying because I was watching it all the time. It took about an hour for this flight to land. The pilots didn't put it down, and they decided that they can land safely, and they at the end they did, as you can see on the bottom left corner. Anyway, we move on. The future. Giannis, should I move on and change my?
It's only 3 slides, so I think we can.
Okay.
Yeah?
Use tell us about the future, and we're going to see anything else.
Yes. So effectively, Fanis showed us how we can see all this information from our own home, independent of the internet, let's say, or how we can contribute to that picture. Now, let's move on and see what are 3 big developments that are on the horizon for the next decade in the area of aviation and air traffic control, which are going to change quite a lot how we fly. So the first one is a little bit behind the scenes or invisible, but it has a potential to affect quite a lot how we learn and improve the aircraft. So if you're aware, the planes carry a couple of data recorders, which are the FDR and CVR. These are usually two separate boxes, and they are painted in a bright color. One is the flight data recorder, which monitors traditionally around 30 variables of the different systems of the plane. And the other is the cockpit voice recorder, which records the communications between the pilots and over the radio with ground control or other planes. They are capable to record multiple hours of data and when a plane crashes, we usually end up searching for them in swamps, in forests, in the bottom of the sea. Sometimes we don't even find them ever. Now, an idea that was tossed a few years ago was, what if we could stream all that data into the cloud? So that no matter where the plane itself ends up, we have the data to comb through them and to try to figure out what went wrong and try to do it better next time. Now, this sounds like a good idea in principle. The problem is it doesn't scale well. So if you think about the bandwidth that we have and the fact that currently the absolute minimum number of variables that they have to record are 88, and in essence, most manufacturers record quite a lot more, close to 300. Then also take into account the cost of the links and the number of planes, like hundreds of planes that a normal airline is operating. This thing will end up using a lot of bandwidth and causing a lot of cost if you want to continuously stream megabytes of data every second to a central location. So instead, somebody thought of a much better idea, which would be to do this trigger-based, so whenever needed only. So this is a very nice diagram on the right of this slide, where you can see the different phases depending on the failure mode of the aircraft. So first of all, you have a normal flight phase. Everything goes well. All systems are nominal. This is like the vast majority of the flights. The system then sends only a very rudimentary set of telemetry parameters, less than 20 parameters, usually basic stuff like engine rotations per minute, fuel, hydraulic pressure, electrical indicators, and all that. And it sends this every 15 seconds. So very little data on relatively sparse intervals. Once the plane detects an abnormal condition, then it starts to send more dense telemetry every 1 second. So it sends the 88 mandatory parameters that the FAA prescribes, and very dense every 1 second. At that point in time, also the engineering team back on the maintenance facility of the aircraft, the airline headquarters is receiving this data, is alerted, and they can also help troubleshoot. This yellow phase can last anywhere from milliseconds in case of controlled flight into terrain to many hours in case you have a slow evolving malfunction. Now, most of the time this is recoverable. But in some cases, the plane reaches a condition where it is doomed. Doomed means the plane is completely outside the flight envelope. So a plane falling vertically, there is no way to turn that around. Or the plane has lost both engines, or you have an uncontrolled fire in the cargo bay, or you have complete loss of hydraulics, or any sort of cascading failure which is non-recoverable. At that point in time, you enter the distress phase, which is the red rectangle in the picture, in the diagram. From that point in time, you have statistically 170 seconds until you crash. So that is where the system kicks in and is attempting to send the content of the flight data recorder and cockpit voice recorder back to base before the plane crashes. It does this by taking control of the highest bandwidth data link that the plane has on board, which is usually the SATCOM link, and starts uploading the data at high volume and with priority and in reverse chronological order. Why is this so? First of all, it gets full control of the link, so it kicks out any passengers using any data services. Secondly, it gets priority routing on the space segment, so on the satellites receiving this signal, and also on the anchor points, so the big ground stations, the big three-floor high satellite dishes where the data link is landing on the ground. And thirdly, it is not sending the data from the red part of the flight. We actually don't care about that part because the plane is already doomed. We know what is going to happen. The most critical data is the yellow part, what happened that led to the catastrophic event. And the most important part of that is the boundary. So we're starting to send from the point of doom or reversely, or trying to send as much data to the past as we can. Now, that can either succeed or send partial data. Once a plane is finally on the ground, either crashed or did a controlled crash landing, if the system is still functional and it has power, it is trying to transmit additional missing data, and also it transmits location information to assist with rescue efforts, much like the emergency transponders. Next one. Sorry, I forgot to mention, this system is not in production. This is undergoing trials now by the FAA, the US. A couple of manufacturers have actually built it, but it is not certified to be used on any planes. Now, to on a more positive note, let's say, what we see historically in terms of passenger volume, and usually it's measured in passenger miles, let's say, billions of passenger miles, is that we have an increasing trend, and it is not increasing linearly. So on average, the number of passenger miles that the airlines log is doubling or tripling every 20 years. This is something that we can account for by building more aircraft or building more airports, but we cannot really scale up how we manage flights in the air until we fundamentally change the underlying principles and procedures behind air traffic control. There are efforts about this both in Europe and the US. In the US, the European Union has a project since like 10 years ago, which is called SESAR, Single European Sky ATM Research, Air Traffic Management Research, which has started to deliver the first pilots, in the metaphorical sense, the first test projects in production. What they are aiming to do is to automate as much as possible of an air traffic controller's job. First of all, removing the need for air corridors, so we will not have highways in the sky anymore. The planes will be able to be freely routed at any point along their route. And it is already done in 30% of France's airspace since a few years. It is also doing automatic flight separation, so the distances in which the planes need to fly one behind the other in the air, and automatic rerouting due to the weather. We might not notice this effect so much in our area, but if you fly in the US and there is a cyclone, for example, you could have a huge chunk of the continental United States forbidden for flying. And this is causing major disruptions in a lot of flights. So this system is aiming to also do automatic rerouting due to the weather, and eventually increase the capacity and airspace utilization, which is the bottleneck that will allow us to switch to higher passenger loads. A third trend that we see emerging is remote control towers. Now you might ask why. The idea is that if you install a bunch of cameras in place of the control tower and also at the end of the runways and in various other critical points around the airport, then you can give a controller better visibility and also make the buildings transparent by using VR. Then you can actually move the controller to a central location and assign one controller to manage 2, 3, 4, 5 regional airports which have only a handful of flights per day. This way, you don't have to pay a couple of controllers on every local small airport, but you can have them centrally and then assign them dynamically to remotely control flights landing and taking off from smaller airports only when needed. This means that you can operate an airport that was previously operating for 5 or 8 hours a day. You can operate it for 24 hours a day, or you can remotely control a small helipad in a remote island. Norway has taken this idea into production, and they are using it in 18 airports, regional airports, small airports since 2022. Next one. Yeah, so this is concluding the basic part of our presentation, and in order to facilitate discussion a little bit, we included also a small quiz. But for this one, we need your participation. Fanny, can you show the, no, present? We don't want the answers.
Yes.
Okay, so first question. What is the strongest system in an aircraft and in your car? Any ideas? You need to be unmuted too. Anybody?
No, I don't think so. Should I press the answer?
Yes. So actually everybody thinks that the engine is the strongest system, but the engine is just producing some power. The brakes are the stronger system. Airplanes and cars can decelerate much quicker than they can accelerate, so it acts as a lever. Next one, what color is an aircraft's black box? That's easy.
Κόκκινο.
Κόκκινο, σωστό. Red or yellow or something that you can see easily.
Πορτοκαλί.
Πυρτικά. Easy. So, next one.
Φορούσε το πορτοκαλί και είναι και θωρίζω, το χτυπάς με το... Είναι σαν τις πινακίδες, τις χτυπάς και φωτίζουν.
How many seconds does it take radars?
Υποβρύχει, ας πούμε, ή ο δίτης με το φακό του και χτυπάει και λαμπυρίζει κατευθείαν για να το δεις.
How many seconds of delay does a radar's picture have? Any ideas? So what you see, is it up to date or does it have some latency?
It has latency.
Yes. So normally it takes 12 seconds for a radar's antenna to go around to do a full rotation, but in fact it doesn't have such a huge latency, comparatively speaking, because as Vassilis pointed out to me, multiple radars track a single airplane most of the time. So especially in dense airspaces like Europe and Greece, you're not as if you are in the middle of the ocean where you have only a single radar from far away. Here, many people see it. Ari, I think I muted you. Can you unmute? Okay. Yeah. Can an airplane land automatically?
Of course.
Of course, yes, true. This is actually done since the 80s, but we're not using it. So it requires some sort of ILS-equipped airport, which less than half of the airports have it, but it is doable.
Αφού οι άλλοι το θυμότανε και οι δύο, λέει.
So pilots still take off and land, but most of the flight is happening through autopilot. Effectively, we could also take off and land with autopilot. What do the numbers at the end of the runway mean? You know, the two numbers that are painted on every runway. Ideas, anyone? So these two numbers are actually the azimuth, the angle with respect to true north. And this is to help planes make sure they land on the right runway, because an airport can have multiple ones. And as a side note, in aircraft carriers, these numbers are always 0, because the ship can turn anyway. It's like they're not going to erase and repaint every 5 minutes. Next one. Does a radar affect snowfall in its area? I cannot count how many times I have been asked about this, especially in our hometown.
Γιατί και ο Φωνής των Τολπιμάτων από εκεί πέρα ανακαλύφθηκε. Ήταν ένας που δούλευε σε ραντάρ και του έλειωσε σοκολάτα και έφτιαξε το φρόνο των Τολπιμάτων. Άρα λογικά θα μπορούσε.
Yeah, in principle it could be, but it is very weak. And also, if it there is an inverse square law which says that radiation is reducing very quickly as you go away. So it will not melt snow, but it will light a light bulb even 100 meters away. But it's no way powerful enough to melt snow. Many people still believe it is. Next one. What are the most common causes of air accidents? Okay, here I want to see you. Nassim?
Human mistake.
Human error,
Yes.
malfunction, system failure, engine failure, wrong data.
Yeah. So the answer is 50% pilot error still. 20% malfunction, like you said, 10% weather, 10% sabotage, which means bombs, hijackings, and all this nice stuff. 10% air traffic control issues, bad instructions, ground failures. By far, it is the human error still. Next one. What are aircraft's tires filled with?
Foam.
Foam. No?
No.
Anybody else?
Τι είναι,
Τώρα τελευταία το βάζουμε και στα αυτοκίνητα, να βοηθήσω λίγο. Τα τελευταία χρόνια βάζουν και στα αυτοκίνητα. Στα λάστιχα του αυτοκινήτου.
Show it.
Δεν έρχεται σε κανέναν.
Άζωτο, nitrogen, so that they don't ignite if they burst. Actually, aircraft tires bursting, it's quite a frequent phenomenon. It's not as seldom as you think, but they have a multiple on its gear, on its landing gear, and it happens, especially when they are landing heavy.
I think there's another reason for this one. It's because the molecules of the nitrogen is bigger than the molecules of the oxygen. So when they inflate the tires, the nitrogen cannot escape from the material of the tires. So the tires maintain their pressure for a longer time. This is the main reason that they inflate the car tires with nitrogen. So I think it's also the same for the tires in airplanes.
Maybe also. I hadn't heard that, but perhaps. Next one. What is an airline's highest financial value asset? The most expensive thing that an airline owns. What is it?
Brand.
Brand, yeah. Well, that's difficult to measure, though.
You're close enough, though.
Mm-hmm. Anybody else? The miles, you don't notice it, the air miles in the loyalty program. Each one of you might have like 10, 100, 200, 500 miles in their loyalty card, but if you multiply it by tens of millions of passengers that a typical regional airline flies every year, you have a stored assets of hundreds of millions. This is more than the value of the planes themselves. And the airlines have also the capability to change the exchange rate in that currency, in their miles, at will. So one day they tell you to fly to Athens, you need 8,000 miles, the next day you need 10,000 miles. Actually, they increased their capital by 20% without even telling anyone. So they basically operate as banks. And this is something that is not very well known. Next one. What is the typical profit margin of an airline? How much percent?
Zero. They make profit from the miles.
That is also possible, yes. It is low. It is pretty low. 9%. For the risks that they take, this is a very low profit margin. And last one, how much more than the co-pilot does an airline captain actually earn most of the time, on average? So you see two people flying the plane, but they are not the same at all. They just wear identical clothes. Any ideas?
Why?
2 to 4 times more. So on small island hopping regional flights, the captain actually earns twice as the co-pilot. In long transatlantic flights, they can actually earn more than 4 times than the co-pilot. This industry is very disproportional. Yeah. The co-pilots are usually very much underpaid. Anyway, so that was all. It took quite a lot, but